हाय विद्यार्थियों, ਤੁਹਾਡਾ ਅੱਜ ਦੀ ਕਲਾਸ ਜਨਰਲ ਆਰਗੈਨਿਕ ਰਿਐਕਸ਼ਨਸ ਵਿੱਚ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਡਿਫਰੈਂਟ ਟਾਈਪਸ ਆਫ ਆਰਗੈਨਿਕ ਰਿਐਕਸ਼ਨਸ ਬਾਰੇ ਵਿਚਾਰ ਕਰਾਂਗੇ ਜੋ ਕਿ ਆਰਗੈਨਿਕ ਕੰਪਾਊਂਡਸ ਵਿੱਚ ਹੁੰਦੇ ਹਨ। ਡਿਫਰੈਂਟ ਆਰਗੈਨਿਕ ਰਿਐਕਸ਼ਨਸ ਨੂੰ ਬੇਸਿਕਲੀ ਚਾਰ ਵੱਖ-ਵੱਖ ਸ਼੍ਰੇਣੀਆਂ ਵਿੱਚ ਵੰਡਿਆ ਜਾ ਸਕਦਾ ਹੈ। ਇਹ ਹਨ substitution reactions, addition reactions, elimination reactions, rearrangement reactions. Let us now discuss these reactions one by one. Let us discuss the first one, that is substitution reaction. Let us try to define it. As the name suggests, it is a reaction in which an atom or a group of atoms is substituted by an attacking reagent. Depending upon nature of the attacking reagent, substitution can be further classified as free radical substitution, nucleophilic substitution, and electrophilic substitution. आओ सब तो पहले ते विचार करिए जेड़ा कि free radical substitution है. Let me give you an example. Halogenation of alkanes is the simplest example of free radical substitution. The general reaction is as shown on the screen. Alkane reacts with halogens in presence of ultraviolet light or heat to form alkyl halide and a halide of hydrogen. This reaction involves a three-step mechanism. These can be listed as: first, chain initiating step. It is a reaction in which a molecular species undergoes homolysis and changes to free radicals. It is always endothermic in nature. The reaction on the screen shows that a hemolytic cleavage takes place in presence of heat or light to form free radicals of halogens. The second one is chain propagating step. It is a reaction in which a free radical reacts with molecular species and gives formation of new free radical and a new compound. Such a reaction can be endothermic or exothermic in nature. For any free radical reaction to be spontaneous, these steps have to be exothermic in nature. In any free radical reaction, the desired product is obtained through the steps shown on the screen. Alkane reacts with halide radical to form alkyl radical and a hydrogen halide. The alkyl radical formed reacts with halogen molecule to form alkyl halide and halide radical. Let us now discuss the third step, which is chain terminating step. These are the reactions in which free radicals combine mutually and give formation of molecular species. These reactions are all exothermic in nature and are taking place parallel to propagating steps. The equation on the screen shows that two halide radicals combine to form halogen molecule. One free radical combines with alkyl group to form alkane. One alkyl group combines with halide radical to form alkyl halide. आओ ਹੁਣ nucleophilic substitution reaction बारे विचार करिए. It is a reaction in which a nucleophilic reagent substitutes another nucleophile from the substrate molecule. This leads to formation of a product belonging to a new family. Let us take an example. in monohalogen compounds, the halogen atom is substituted by nucleophilic reagents. Let me tell you that for these reactions to be spontaneous, the attacking nucleophile has to be stronger than the nucleophile to be substituted. आओ हुण mechanism of nucleophilic substitution reaction ते नजर मारिए. In this substitution, there is duality in mechanism. As in certain substitution reactions, the rate of reaction is dependent on concentration of nucleophile, while the rate in certain other substitution reactions is independent of the concentration of nucleophile used. These two mechanisms are termed as nucleophilic substitution unimolecular or SN1 and nucleophilic substitution bimolecular or SN2.
आओ हुण SN1 रिएक्शंस बारे विचार करिए जो कि न्यूक्लियोफिलिक सब्स्टिट्यूशन यूनिमोलिकुलर रिएक्शन है. It is a complex reaction involving two-step mechanism. In first step, heterolysis of carbon-halogen bond takes place, resulting in the formation of carbocation intermediate. In second step, carbocation formed combines with nucleophilic reagent and results in formation of a substitution product. Since in complex reactions, slowest step is rate determining step and first step is relatively slower than the second. Therefore, reaction rate in such reactions depends only upon the concentration of substrate that is reacting alkyl halide, or in other words, we can write as rate is equal to a constant multiplied by concentration of alkyl halide as shown on the screen. आओ हुण bimolecular reaction nucleophilic substitution बारे जानिए. It can be defined as an elementary or a single-step reaction. In this reaction, nucleophilic reagent reacts with the carbon from the opposite side of halogen. Reaction passes through a transition state in which there is partial bond formation of nucleophile with carbon and partial bond cleavage of halogen from carbon. Through transition state, there is formation of substitution product. As it is a single-step reaction, rate of this reaction depends upon concentration of both substrate and nucleophilic reagent, or we can say that rate is equal to constant K multiplied by concentration of alkyl halide multiplied by concentration of nucleophile as you are seeing on the screen.
आओ हुण factors determining mechanism of SN reactions बारे विचार करिए. Nucleophilic substitution reaction ਦਾ mechanism screen ਤੇ ਵਿਖਾਏ ਜਾ ਰਹੇ factors ਤੇ ਨਿਰਭਰ ਕਰਦਾ ਹੈ. Nature of substrate, nature of nucleophilic reagent, nature of solvent, nature of the leaving group. ਸਭ ਤੋਂ ਪਹਿਲਾਂ nature of substrate ਬਾਰੇ discuss ਕਰਦੇ ਹਾਂ. Those alkyl halides which lead to the formation of stable carbocation by heterolysis of carbon-halogen bond will follow SN1 path in their substitution reactions. As stability of carbocation follows the order 3 degree is more stable than 2 degree is more stable than 1 degree, which is more stable than methyl group as shown on the screen. Therefore, towards SN1 reactions, the reactivity order of alkyl halides will be as shown on the screen. 3-degree halide is more stable than 2-degree halide, which is more stable than 1-degree halide, which again in turn is more stable than methyl halide. Similarly, in case of SN2 reactions, reactivity of halide depends upon stability or the energy of the transition state. If in the transition state, carbon atom is sterically crowded or is surrounded by bulkier groups, then the potential energy of transition state is high and SN2 path is less favored. Conversely, if in transition state, carbon atom is not sterically crowded or is surrounded by small-sized atoms or groups, then potential energy of transition state is low and SN2 path is highly favored. On this basis, reactivity order of different halides by SN2 path is as shown on the screen.
3-degree halide is less stable than 2-degree halide, which is less stable than 1-degree halide, which is less stable than methyl halide. In SN2 reactions, the nucleophile has to approach the tetrahedral carbon involved in carbon-halogen bond, that is CX bond. The presence of bulky groups around the carbon atom hinders that attack of the nucleophile. 3-degree halide is less stable than 2-degree halide, which is less stable than 1-degree halide, which in turn is less stable than methyl halide. Therefore, the order of reactivity is as shown on the screen.
आओ ਹੁਣ नेचर ऑफ न्यूक्लियोफिलिक reagent ਤੇ ਵਿਚਾਰ ਕਰੀਏ. Nucleophilic reagents, which are strong nucleophiles or which have high nucleophilicity, favor SN2 reactions, and the nucleophiles, which are weaker with low nucleophilicity, cause SN1 reactions. ਅਸੀਂ ਹੁਣ nature of solvent ਤੇ ਵਿਚਾਰ ਕਰੀਏ. Polar protic solvents have high dielectric constant, which helps in heterolysis of carbon-halogen bond. Always favor SN1 reactions. Polar aprotic solvents, which can effectively solvate only cation of nucleophilic reagent, increase nucleophilicity of attacking nucleophile and favor substitution by SN2 path.
Few polar solvents are water, ammonia, ethyl alcohol, acetone, dimethyl sulfoxide, dimethyl formamide, etc. Few non-polar solvents are carbon tetrachloride, carbon disulfide. Few polar protic solvents are water, ammonia, ethyl alcohol, etc. Few polar aprotic solvents are acetone, dimethyl sulfoxide, dimethyl formamide, dimethyl acetamide, etc. ਅਸੀਂ ਹੁਣ nature of leaving group ਤੇ ਵਿਚਾਰ ਕਰੀਏ. Reactivity of any compound in substitution depends upon leaving ability of the group to be displaced. Leaving ability depends upon the strength of the base to be removed, as weak bases are good leaving groups. On this basis, in this substitution, reactivity of different halides is as shown on the screen. Children, this means that alkyl iodide is more reactive than alkyl bromide, which is more reactive than alkyl chloride, which is more reactive than alkyl fluoride. आओ हुन stereochemistry of SN2 reactions दे बारे जानिए. As in these reactions, the attack of nucleophile is from opposite side of halogen. There is inversion of configuration if reaction is taking place at chiral center or at asymmetric carbon. This inversion of the product formed when substitution is taking place over chiral center is called inversion of configuration or Walden inversion. The configuration of the tetrahedral carbon involved in the reaction gets inverted, just like an umbrella, because the nucleophile, that is the hydroxide ion, gets attached to the opposite side. This is inversion of the product formed.
Let us now learn about stereochemistry of SN1 reactions. In our reactions which carbocation intermediate heterolysis of carbon halogen bond ਦੇ ਕਾਰਨ ਬਣਦਾ ਹੈ. ਜਿਵੇਂ ਕਿ ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ, carbocation sp2 hybridization ਦੇ ਕਾਰਨ ਫਲੈਟ ਜਾਂ ਪਲੇਨਰ ਹੁੰਦਾ ਹੈ. ਇਸ ਲਈ ਨਿਊਕਲੀਓਫਾਈਲ ਪੋਜ਼ਿਟਿਵਲੀ ਚਾਰਜਡ ਕਾਰਬਨ ਨਾਲ ਪਲੇਨ ਦੇ ਦੋਨੋਂ ਪਾਸਿਆਂ ਤੋਂ ਜੁੜਨ ਦੀ ਪ੍ਰੋਬੇਬਿਲਿਟੀ ਬਰਾਬਰ ਹੁੰਦੀ ਹੈ. ਇਸ ਦੇ ਕਾਰਨ ਕਾਰਲ ਮੋਲੀਕਿਊਲ ਦੋ ਡਿਫਰੈਂਟ ਕਨਫਿਗਰੇਸ਼ਨਸ ਵਿੱਚ ਬਣਦਾ ਹੈ. ਇਸ ਨੂੰ ਰੈਸਿਮਾਈਜ਼ੇਸ਼ਨ ਆਫ ਪ੍ਰੋਡਕਟ ਵੀ ਕਿਹਾ ਜਾਂਦਾ ਹੈ. Generally, in these reactions, product is partially racemized and extent of racemization depends upon dielectric constant of the solvent. ਆਓ ਹੁਣ electrophilic substitution ਬਾਰੇ ਸਿੱਖੀਏ. It is a reaction in which substitution is caused by an electrophilic reagent. Substitution of hydrogen atom as hydrogen ion from benzene by an electrophilic reagent is an example of electrophilic substitution reaction. Benzene ring is a source of electrons as it has pi electron cloud of 6 pi electrons lying above and below the plane of the molecule. Any electron-seeking reagent can cause substitution of hydrogen ion from any carbon atom of the ring to form substitution product. ਆਓ ਹੁਣ electrophilic substitution ਦੀ general mechanism ਤੇ ਵਿਚਾਰ ਕਰੀਏ, ਜੋ ਕਿ ਸਕਰੀਨ ਤੇ ਵਿਖਾਈ ਜਾ ਰਹੀ ਹੈ. Electrophilic substitution happens in many of the reactions of compounds containing benzene rings, the arenes. For simplicity, we'll only look for now at benzene itself. This is what you need to understand for the purpose of the electrophilic substitution mechanisms.
Benzene C6H6 is a planar molecule containing a ring of 6 carbon atoms, each with a hydrogen atom attached. These are delocalized electrons above and below the plane of the ring. The presence of the delocalized electrons makes benzene particularly stable. Benzene resists addition reactions because that would involve breaking the delocalization and losing that stability. Benzene is represented by the symbol on the screen, where the circle represents the delocalized electrons and each corner of the hexagon has a carbon atom with a hydrogen attached.
Benzene and electrophiles. Because of the delocalized electrons exposed above and below the plane of the rest of the molecule, benzene is obviously going to be highly attractive to electrophiles, species which seek after electron-rich areas in other molecules. Electrophile ਜਾਂ ਤਾਂ ਇੱਕ positive ion ਹੋਵੇਗਾ ਜਾਂ slightly positive end of a polar molecule ਹੋਵੇਗਾ. Benzene molecule ਵਿੱਚ plane ਦੇ ਉੱਤੇ ਅਤੇ ਥੱਲੇ ਜਿਹੜੇ delocalized electrons ਹੁੰਦੇ ਹਨ ਉਹ reactions ਲਈ available ਹੁੰਦੇ ਹਨ. If benzene underwent addition reactions, it would need to use some of the delocalized electrons to form bonds with the new atoms or groups. This would break the delocalization and this costs energy. In most of benzene's reactions, the electrophile is a positive ion, and these reactions all follow a general pattern.
The general mechanism. The first stage. Suppose the electrophile is a positive ion. Let us call it as X positive ion. Two of the electrons in the delocalized system are attracted towards the X positive ion and form a bond with it. This has the effect of breaking the delocalization, although not completely. The ion formed in this step isn't the final product. It immediately goes on to react with something else. It is just an intermediate. There is still delocalization in the intermediate formed, but it only covers part of the ion. ਜਦੋਂ ਤੁਸੀਂ ਇਹਨਾਂ ਵਿੱਚੋਂ ਕਿਸੇ ਵੀ mechanisms ਨੂੰ ਲਿਖਦੇ ਹੋ ਤਾਂ draw the partial delocalization to take in all the carbon atoms apart from the one that the X has become attached to. Intermediate ion positive charge carry ਕਰਦਾ ਹੈ ਕਿਉਂਕਿ ਤੁਸੀਂ ਇੱਕ neutral molecule ਨੂੰ ਇੱਕ positive ion ਨਾਲ join ਕਰਦੇ ਹੋ. ਇਹ ਰਿੰਗ ਦੇ delocalized part ਦੇ ਉੱਤੇ positive charge spread ਹੁੰਦਾ ਹੈ. Simply draw the plus in the middle of the ring. The hydrogen at the top isn't new. It's the hydrogen that was already attached to that carbon. We need to show that it is there for the next stage. The second stage. Here we have introduced a new ion, Y negative. Where did this come from? You have to remember that it is impossible to get a positive ion on its own in a chemical system. So, Y negative is simply the negative ion that was originally associated with X, positive X ion. Don't worry about this at the moment. It's much easier to see when you have got a real example in front of you. A lone pair of electrons on Y negative forms a bond with a hydrogen atom at the top of the ring. That means that the pair of electrons joining the hydrogen onto the ring aren't needed anymore. These then move down to plug the gap in the delocalized electrons, so restoring the delocalized ring of electrons which originally gave the benzene its special stability. To sum up, we can show the reaction of benzene with an electrophile and the delocalization of electrons as shown on the screen. All three structures can be represented by a aranium cation, which further loses a hydrogen ion to form a substitution product.
ਅੱਜ ਅਸੀਂ ਜਨਰਲ ਆਰਗੈਨਿਕ ਰਿਐਕਸ਼ਨਸ ਬਾਰੇ ਜਾਣਿਆ. ਅਸੀਂ ਸਿੱਖਿਆ ਕਿ ਆਰਗੈਨਿਕ ਰਿਐਕਸ਼ਨਸ ਨੂੰ ਸਬਸਟੀਟਿਊਸ਼ਨ ਰਿਐਕਸ਼ਨਸ, ਐਡੀਸ਼ਨ ਰਿਐਕਸ਼ਨਸ, ਐਲੀਮੀਨੇਸ਼ਨ ਰਿਐਕਸ਼ਨਸ ਅਤੇ ਰੀਅਰੇਂਜਮੈਂਟ ਰਿਐਕਸ਼ਨਸ ਵਿੱਚ ਕਲਾਸੀਫਾਈ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ. We first learned about substitution reactions. ਅਸੀਂ different examples ਦੀ ਮਦਦ ਨਾਲ free radical substitution, nucleophilic substitution ਅਤੇ electrophilic substitution ਬਾਰੇ ਸਿੱਖਿਆ. ਅਸੀਂ ਵੇਖਿਆ ਕਿ free radical substitution reaction 3 steps ਵਿੱਚ ਹੁੰਦਾ ਹੈ. the chain initiation step, chain propagating step, and the chain terminating step. We then discussed nucleophilic substitution reactions, that is SN1 and SN2 reactions, and their mechanism. We also had a look at the factors determining the mechanism of the substitution reactions and the nature of the nucleophilic reagent and the nature of the leaving group. We then discussed stereochemistry of SN1 and SN2 reactions. In the end, we discussed about electrophilic substitution and reactions in aromatic compounds. Children, so we have come to the end of today's topic. Let me now ask you few questions to check your understanding.
My first question is, which out of the structures shown on the screen will undergo SN1 reactions faster? And the answer is tertiary butyl chloride upon ionization will form a tertiary carbocation which is more stable than the secondary carbocation which will be formed upon the ionization of secondary butyl chloride. This means that tertiary butyl chloride is more reactive in this case. My next question is, which out of benzyl chloride and chlorobenzene will undergo SN1 reaction faster? And the answer is benzyl chloride is more reactive towards SN1 reactions than chlorobenzene because it readily ionizes to give benzyl carbocations which is resonance stabilized. Now let us discuss about reactivity of chlorobenzene. In chlorobenzene, ionization leads to very unstable carbocation formation. Therefore, it is less reactive than benzyl chloride. My next question is, explain why allyl chloride is more reactive than N-propyl chloride towards nucleophilic substitution. And the answer is allyl chloride is more reactive than N-propyl chloride towards nucleophilic substitution reaction, SN reaction, as it readily ionizes to give resonance stabilized carbocation. The other compound, N-propyl chloride, forms less stable carbocation. Hence, it is less reactive. My next question is, predict the substitution product of the reaction shown on the screen. Answer. Have a look at the equations on the screen. Please note that the product of the reaction is 2-methylbutane-2-ol instead of the 3-methylbutane-2-ol because rearrangement of intermediate carbocation occurs due to 1,2 hydride shift. Thus, 2-methylbutane-2-ol is formed instead of 3-methylbutane-2-ol.
ਬੱਚਿਓ, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। Thank you for your attention and see you next time.